converted to mass. It works both ways. So what was mentioned was that you can say that mass can be converted to energy, but at the same time, energy can also be converted to mass. They are interchangeable. And then when it comes to finding the energy associated with conversion of mass or mass changes, we generally have this equation where E is equals to delta mc squared. So this one was the equation that you primarily used in the last lesson. And then I mentioned to you that when you want to use this particular equation, it can be used in different contexts, specifically two different contexts. Either you can use it to find binding energy, then this one, it will be E delta mc squared, but the delta m is actually the difference in mass between nucleus and the nucleons. This is the difference. This is what the delta m, or rather the mass defect, is supposed to tell you. Then at the same time, I'll also tell you that rather than finding binding energy, you can also use it to find energy release in a nuclear reaction. Okay, where you will still use E is equals to delta mc squared, but your delta m here is the one that's a bit different. Okay, your delta m here is actually the difference in mass between product and reactant. Okay, in general, the equation used is the same, but there is a difference in terms of what delta m is. Both are talking about different in masses, but in terms of what is different here, they are actually different things, okay, depending on the context of the question. So this was what I mentioned to you in the last lesson. All right, so if you were to look at just page 40 right now, okay, page 40, this is a good example to go through. So we tell you there's a possible nuclear reaction taking place, which is given by this, and then data for the nuclear in the reaction is given by this. Show that the energy equivalent to a mass of 1U is 934 mega eV. So this one, we've done the example before. So this one, I think I can just breeze through it. So let me just open it out. This is November 19 P41. This is what we have, you know. Okay, where's the question? The question should be all the way at the end. Okay, right. So show that the energy equivalent to 1U is actually 934 mega eV, right? So if you have a mass difference of 1U, how much is actually the energy associated with it? This one you can actually just use E is equals to delta mc squared, your mass difference being U, and then your speed of light square. You just sub in your values of U, which is 1.66 times 10 power minus 27, sub in the speed of light, square it, and then you're going to get this answer in joules. But the answer wants it in EV, mega EV. So you have to take the answer in joules, divide by 1.6 times 10 power minus 19 to get the answer in EV in the first place. So this is the answer you'll get if you go and change it to times 10 power 6. But here you need to have mega, right? So you already made it into 10 power 6 here. This one automatically becomes 934 mega EV because mega is by right times 10 power 6. Okay, so this one is very simple. We've done this example quite a number of times. You'll notice that this is something they always keep asking. Now, part B1, this one is slightly different. Use data from figure 12.1 to calculate the binding energy per nucleon of a nucleus of uranium-235. So what is the binding energy for this particular nucleus here? Now, if you look at figure 12.1, they ask you to look at figure 12.1, which is this one. What is the binding energy per nucleon of uranium? Okay, so you see right over here, they've already given you the mass of the nucleus. Okay, maybe I use a different color. They've given you the mass of a nucleus itself, and then this one, they give you the mass of the nucleons. In other words, if I try to write it out for you, this one is actually the mass of your nucleus. This one is the sum of the mass of your nucleons. Okay, so you see there's a difference in the mass here, which is reflected over here. Okay, the difference in the masses is 1.865 U. Okay, so this difference in mass was actually converted into energy. All right, so I mentioned to you last time, when you're talking about binding energy, it is talking about the amount of energy that you need to separate a nucleus into individual nucleons completely to infinity. What we mean by that was that if this one was your nucleus, and I tell you that there are 2 neutrons and 2 protons here, if you separate them into the individual nucleons, this one will be 2 neutrons, 2 protons here. Whatever energy that you took to separate this nucleus into the individual nucleons, this one will be the binding energy. Okay, so in the process of you going from here to here, it involves a change in the mass. Okay, I mentioned to you that time before that the mass of the nucleus, if you were to compare with the mass of the nucleons, they are not going to be the same. Actually, mass of the nucleus will actually be less than the mass of the nucleons itself. Okay, so when you go and break off your nucleus into your nucleons, you are putting in energy, you're converting back the energy into mass. All right, so the difference in mass here between nucleus and nucleons is an indication of the energy that you have put in to separate your nucleus. So that is your binding energy by definition. So you know that your difference in your mass is 1.865 U, and you already found out here 1 U is actually worth 934 mega eV. So you want to find the binding energy of uranium, this one here, you take the mass defect multiply by 934. This one will give you your binding energy. You will need 1741.91 mega eV. Okay, but the question wants it in terms of per nucleon. You see, you have to take your binding energy divide by the number of nucleons to get binding energy per nucleon. Okay, so let me just write it here. If you want to get BE per nucleon, this one will be just BE divided by your nucleon number. Okay, nucleon number for uranium is 235, which you can see from here. Okay, so your final answer will be that 7.41 mega eV, just like that. Okay, so that one is done. Then we go on to the next one. All right, now, if you look at the bottom portion here, wait, let me just erase a certain thing. The nucleon number or isotope of element rutherfordium is 267. State whether the binding energy per nucleon is going to be, of this isotope, is going to be greater, equal to, or less than the binding energy of uranium-235. Okay, so this one is what you have. This one, to answer this, you have to refer back to your diagram for binding energy per nucleon versus nucleon number. So this one, you remember this little curve, and that the peak always belongs to 56. So uranium-235 will probably be somewhere around here. But rutherfordium is 267. 267 is actually more than 235, right? Okay, uranium is 235. Rutherfordium is 267. So actually it should be somewhere around here. Okay. Hey, wait. Yeah. So rutherfordium will be somewhere around here at 267. So the question is asking you what is the binding energy per nucleon. So for uranium, it was somewhere around here, but for rutherfordium is somewhere around here. You see the value is lower. Okay, so that's why the answer is going to be lesser. All right. Okay, so this is one part. Then after that, this one is okay. Then we go on to the next one. Next question. Okay, so this is where you need, there's some difference here. This is something I need to highlight to you when it comes to using binding energy, when it comes to finding energy release. Okay, so if you look at part C, okay, you look at part C, which is on the next page, just look at that part. The following part asks you to find out the energy release in the nuclear reaction. Okay, so find out the energy release in the nuclear reaction here. Okay. Now, when you talk about the nuclear reaction, they're actually talking about this nuclear reaction here. This one changing to, say, this one. Okay. So this one by right would be your reactants. Wait, let me use a matching color. This one by right would be your reactants. And then this one by right would be your products. Okay, so same thing here. That time I also mentioned to you, when you go and have some sort of nuclear reaction going from reactants to products, you will tend to have mass changes. Okay, and your mass changes here actually get converted into energy. Okay, so that energy is your energy release here, which you're trying to find out. Okay, so that time if you have a difference in mass between reactants to product, that time it was mentioned to you that you can use this equation. Okay, I mentioned to you that you can use this equation to find the energy release during a nuclear reaction. You can use where E equals to delta mc square, where your delta m is just the sum of the masses of the product minus of the sum of the masses of the reactant. Okay, so this was what we did last time. Okay, but here we cannot use this method. Okay, you actually did this method in one of the previous questions. Let me just try to find out where it was. It was one of the earlier questions. Was it 25 or 20? Just give me a second. Was it 25? No. Was it 20? It's one of the earlier ones. Just let me see where it is. 17, 18, 15. Wait, huh? 17, 18. Yeah, okay. There's an example here that you can see. This one would be page 19. Okay, page 19 was actually something that we did before. All right, I'm just gonna open it up just so you can see some sort of comparison here. June 17, P41. Is it 41? Wait, yeah, P41. Okay, so if you look at page 19, the thing that I just want to highlight to you is this. Now you look at the equation in page 19 of your worksheet. They give you at that time, this is page 19, okay? This is page 19. At that time, they told you there was a nuclear reaction, uranium plus neutron, giving you molybdenum, lanthanum, 2 neutrons, and then 7 electrons, okay? Then after that, the subsequent question asks you to find out what was the energy release in the reaction. You know, if you look at the next page of page 19, the next thing they asked you to do was that find out the energy release in this reaction and then give your answers to 3SF. So for this particular part here, you notice that we were actually kind of using E is equals to delta MC square. Okay, we were using this particular question. We were using this particular equation where we try to find out the difference in mass between the products and the reactants. And then after that, we say that, since we know the difference in the mass, we just multiply with the energy of 1U, then we're going to get the energy released in the reaction. So for this particular question, we were actually using this method over here. Okay. Now, if you now look at page 40, look at page 40 and look at the equation that is given to you. If you look at page 40, you see this question here, this equation here. Notice that this equation is actually exactly the same as the one that you're seeing in page 19. It's exactly the same. Okay, same equation, same reaction. And then for this question here, at the next page, they're asking you to find out the energy released in the nuclear reaction. But you notice that you are not using the method that is used previously. You're not using this method here, where you find the difference in mass between the product and reactants. Instead, you seem to be using something else entirely here. Okay, now, the reason why we say that, the reason why we cannot use that method right now is because we do not know the full masses. Okay. Wait, okay. Right. So you see, if you look at the equation right now, you do not know the full masses. Sorry, Yongqi, just give me a minute. My nephew is crying. 1 minute. Okay.
Oh, okay.
All right. Okay. Right. Right. Sorry for the interruption. Back. Okay. Right. So back to what I was talking about just now. We cannot use E equals to delta MC squared to find the energy released in this current reaction. Okay, because we do not know the masses. We do not know the full value of the masses. Okay, what do I mean by I do not know the full value of the masses? You look at the products and reactants right now. These are my reactants. And then these are my products. Okay. Do I know the value of uranium? Yes, I do, because the value is given here. Do I know the value of mass for neutron? You don't see the values given here, right? So this one is missing. Do I know the value of mass for molybdenum? This one I also know because it's given right over here. Okay, but for lanthanum is also given. All right, so molybdenum and lanthanum are given. Neutron, again, you see is the problem here. We do not know the mass of the neutron. And then likewise, we also do not know the mass of the electron. You see, there are actually some missing masses here that we do not know. All right, so we cannot proceed with the methods that we used previously, which is E equals to delta MC squared, because we do not know the full value of the masses. So we cannot find out what is the actual value in the difference in the mass. If you look at page 19, the one that you did previously in the last lesson, you actually had the full value of all the masses, including the neutron, including the electrons. So here in page 40, you actually do not know neutron and electron. You do not know the full value, so you cannot find delta M accurately. So you cannot use E equals to delta MC squared here. All right, that's the reason why you cannot use that method. So instead of using E equals to delta MC squared, you actually have to use a different method right now, which is what is shown here in your screen. Okay, here you have to use instead binding energy of product minus binding energy of reactant. Okay, so this one here, the reasoning why I can say this energy release is binding energy of product to binding energy of reactant is because of this. You can just think of it as this. Now, there are some facts that you need to remember to help you understand. BE is energy required to separate a nucleus into individual nucleons to infinity. Okay, so this is one thing that you just remember first. BE by right is normally defined as whatever energy that you took to separate a nucleus into individual nucleons to infinity. Okay, that's number one. And then after that, there's another fact here that I needed to mention to you. The goal of any nuclear reaction is always to become more stable. Okay. Now, when something is more stable, you learn in chemistry, that means you are at lower energy level. Okay. This is something that you learn in chemistry. When something is less stable, it's at higher energy level. But when something is more stable, it is at lower energy level. Okay. Okay, so this is what you have. Okay, now how does all this tie to you understanding what is energy release? So let's just say, for example, I tell you, I give you 2 lines, or rather 3 lines right now. This line represents the energy level at infinity. Okay, this line represents the energy level at infinity. And then after that, this line represents the energy level of, say, your reactant. Okay. So this one here is basically, if you're going down your direction here, this one means you are getting more stable. Okay, because this one is your energy level diagram. Okay, this one, let me just write it here. This one, you can just think of it as your energy level diagram. Okay, you've probably seen this in chemistry before. Okay, so the top one is usually when you're talking about energy level at infinity. You normally see this when you're talking about energy level of electrons, all right, in chemistry. So the topmost one usually is at infinity. This is the highest energy level. Okay, then after that, say right now, reactant is here right now. If I want to draw a line for the products, the product line, the energy level representing the products will usually be lower. Okay, it will usually be at the lower part here. Okay, this one is representing your products. Okay, because usually, as I mentioned to you, any nuclear reaction that occurs, the goal is always to become more stable. In other words, it will go to a lower energy level. So that is represented by the line that I just dropped, labeled product here. It's going to be at lower level. Okay, so here's the thing. If this is the energy level diagram representing infinity, reactant, and product, if I want to look at the binding energy, because binding energy, as I mentioned to you, was whatever energy that you need to separate a nucleus into individual nucleons completely to infinity, right? So you imagine this, if my reactants is represented here, and then I want to separate the nucleus of the reactants into the individual nucleons to infinity, the binding energy of my reactants would be this one. This is PE of my reactant. Okay. So likewise, if I'm talking about the binding energy of my products, it will be, I think this one I should draw it outside. Okay. This is the BE of my reactant. And then this one here for products, this one will be representing the, sorry, I need to use a different color, same color. Okay. This one would be representing the BE of my products. Okay, so this one represents the BE of my product. Okay, so you notice that in terms of the BEs, the amount is actually kind of different when you look at the length. Okay, so when it comes to actually finding out the energy release, your energy release during the reaction is actually represented by this line here. The difference between this the pink and blue line. This is where your energy, the difference here is your energy release. Okay, this portion here is your energy release, which incidentally is actually the difference between your reactants, BE of your products and reactants. No? That's why you see here, when I try to find out the energy release, I'm actually trying to take the BE of my products minus of the BE of my reactants. Okay, now so far from this diagram, can you understand the concept?
Yeah.
Okay, right, so this is another way. All right, so to find energy release in a nuclear reaction, you can use E equals to delta mc squared, provided you know the full value of the masses. But if you do not know that the full value of the masses, you will have no choice but to use this BE of product minus BE of reactant. Usually it's either these two methods. Okay, so this one here, maybe I can also write it somewhere. To find energy release in a nuclear reaction, you either use E equals to delta mc squared. Maybe you can also just write it here as something like a addition to this, or you can actually just say E is BE of the product minus the BE of your reactants. Okay, just find the difference between those two and you should be fine. Okay, either these two. All right, so here you want to find the BE of the product and then BE of your reactants. Now, can you find the BE of your products and reactants given from your question? Yes, you can, because you have the full information from your table. Okay, so because just now, remember I told you that BE per nucleon is actually your BE over nucleon number. Wait, just now I wrote it here. BE per nucleon is actually BE over nucleon number. So from here, it could also mean this. Binding energy is actually binding energy per nucleon times nucleon number. Okay, so you can actually kind of find out your answer right now. Okay, because you see, you have BE per nucleon given inside your table. All right. Now, just now there was an empty blank here, right? 7.142. This one is actually what you have here found in the question B1. All right. So if you have binding energy per nucleon and you have the nucleon number, you can actually multiply those two together to find the BE for the respective nuclei. Okay. So let's just say for uranium now, for example, if I want to find the BE of uranium, I will take 235 multiplied with 7.412. That one will be the BE of the uranium. If I want to find for molybdenum, I will take 95 multiplied with 8.443. And then if I want to find for lanthanum, I will take 139 multiplied with 8.189. Okay, so these three things, you can find the BE. Now, what about the BE of neutron and electron? Okay, so just now one of the problems was that I mentioned to you, they never give you the masses of your neutron and electron, right? So now, singling back the neutron and electron, is there any BE for neutrons and electrons? Bearing in mind that BE by default was defined as whatever energy that you need to separate a nucleus into individual nucleons. It tells you is the energy that you need to separate something into smaller pieces. So you look at this, neutron is actually already a nucleon by itself. You cannot separate it into even smaller part. It's already a nucleon because BE by right, you are trying to separate a nucleus into nucleons. Nucleon was the smallest part that you're supposed to separate it to. Here, neutron itself is already a nucleon. You cannot separate anymore. So this one, neutron is already a nucleon itself. Therefore, BE is actually 0 for neutron. Okay. Okay, so this one, for these two, neutron is already a nucleon, the B is 0. So electron itself cannot be separated already. Although it's not a neutron, it cannot be separated anymore. So this one, electron cannot be separated. Therefore, BE is also 0. Okay. So just now I mentioned to you, you are supposed to find the BE of your reactant. And then after that, you were supposed to find the BE of your product. The difference in the BEs is actually your new energy release. But when you sum it up, just be careful that there are some components that do not have BE. The neutron does not have BE, neither would the electron. Okay, so you see later on in the workings, when you're talking about the BE, you're really only doing these three. You're only considering those three, which is what you see in the workings right over here. Okay. So wait, let me just erase. Okay, so you notice that there are only three terms here. That is because I only consider uranium, molybdenum, and lanthanum. Okay, so this one was the BE of my products. This one here is the BE of my reactants. Eventually.
Wait, to recap, neutron, cause they're already neutron, then cannot separate.
Yes, because BE is you're trying to separate a nucleus into nucleon, right? Nucleon was supposed to be the smallest part that you're separating to, right? Okay, but right now you look at the equation, the neutron is actually already a nucleon itself. You cannot separate it into another nucleon, right? It's already the smallest part you can get, isn't it?
Yeah.
Okay, so you cannot separate into a nucleon anymore. So it's already BE 0. Okay.
So electron also same concept.
Electron also same concept.
Small.
Okay, although electron is not a nucleon, but electron by itself is already, it's just an electron. It cannot be separated, right? By definition, we have not learned anything thus far that tells you that you can separate an electron, right, into smaller parts. No, right? Electron by right is your smallest possible particle. So electron also, even you want to apply the concept of BE, which is energy required to separate it into smaller parts, you notice you cannot apply it because it's really the smallest possible particle. So BE is also 0. Okay?
Okay.
Right. So that one done, you just sub in all the values. Eventually, you get the answer as 199 mega EV. Okay. So that one is done. Then after that, okay. Right. Yeah, so then after that you look at part D. Part D, this one I think is pretty straightforward. Okay, for part D, they tell you that the nuclei in 1.2 times 10 power 7 moles of uranium-235 all undergo the reaction in a time of 25 milliseconds. Calculate the average power released during a time of 25 milliseconds. Okay, so think about what they're talking about. The nuclei in this amount of mole of uranium-235 all undergo the reaction in a time of 25 milliseconds. Calculate the average power released during the time of 25 milliseconds. Okay, now if you relate to what you've learned in AS physics, when we talk about power, power is strictly speaking defined as energy over time, or in your current case, total energy released over total time. Now, total time, you can easily see that it is 25 milliseconds. That's why it's divided by 25 times 10 power minus 3. But what about your energy release? Okay. Now, you think about it. In your current case, you've already found energy release in mega EV during this nuclear reaction. But this amount of energy is correct to say is only for one uranium-235 nucleus only. Okay, it's only for one uranium-235 nucleus only. Okay, because you see this reaction here. One uranium nucleus, when it interacts with a neutron, gives you this and 934 mega EV. Okay, so whatever energy you calculated is actually only for one nucleus, one uranium nucleus. Okay, so what they're telling you now is that your total nuclei is all inside this amount of moles. Okay, so you have to find out in the first place 1.2 times 10 power minus 7 mole, how many nuclei, how many uranium nuclei does it contain? And if one uranium nuclei gives you 199 mega EV, you times the number of nuclei times the energy of one nuclei, you're going to get the total energy release. Okay, so that's why here you see to find the number of reactions in 25 milliseconds, I took the number of moles, I multiply with the Avogadro constant. Okay, because I think this one worded another way is just this now. Number of moles is your number of nuclei times Avogadro constant. Number of nuclei is your number of moles times your Avogadro constant. You can think of number of reactions here as finding the number of uranium-235 nuclei. Okay, so this is the number of uranium-235 nuclei. So from there, you translate it to total energy release. No? So 7.224 times 10 power 6. If the energy is 199 mega EV, you get rid of the mega, you get rid of the EV to change it to joules. So eventually you multiply everything in, you're going to get the answer as 9.2 times 10 power 7 watts. Okay, so far so good.
Yeah.
Okay, right. So this is one part for calculation. Yeah, the calculation here a bit tedious, but I think as you keep doing, you notice that the calculations are pretty straightforward. It's like doing chemistry questions. That's the impression I'm getting now. All right. Okay, so this one is okay. Then after that, we did page 40 just now. So let me just go back to some of the others one. Page 40 be done. What about page 34? Is doable, but let me see. Okay, I think we just do 34. Right, 34. Let's just have a look at page 34 since it's something to do with what I mentioned earlier. Okay, let's have a look at page 34. This is November 18 P42. Okay, what is meant by nuclear fission? What is what is meant by nuclear fusion and fission? This one is something that you've learned from your definitions. It's something that you can see from your notes, the definition. So this one, I think I'll just go through it very quickly. Nuclear fission is just simply when two light unstable nuclei combine to form a heavy stable nucleus. That's all there is to it. And then nuclear fission is when a heavy unstable nucleus absorbs neutron and then splits into two daughter nuclei of about equal masses and more neutrons to become more stable. Okay, so this is your definition. All right, you just copy the definition from the notes. This one would be usable for all circumstances when they ask you for nuclear fission and fission. Okay, right? So this one is something that you could understand also from your time in SPM. So this one I don't think I need to explain that much. All right, now for part B, they ask you a nuclear reaction which may occur in the future, which may in the future be used for the generation of electrical energy is this, where you have two hydrogen isotopes, deuterium and tritium, fused together to give you helium or alpha particle. Okay, this is actually talking about nuclear fusion. You see two light nuclei form a heavier nucleus. This is actually talking about fusion. All right. Now they ask you, find out what is actually particle X. All right. So all you just need to do is you go and balance off the proton number and neutron number on both sides. If this one is 2, this one is 2, this one obviously will be 0. Okay. And then after that, you look at the top portion, neutron number. If this one is 5, and then this one is 4, this one must be 1, so that it becomes 5 in total. So this X is 0, 1. So the only thing that has 0, 1, where your proton number is 0 and neutron number is 1, is actually a neutron. Okay, so particle X is actually neutron. Okay, so this one is pretty straightforward. Okay, then the next thing that we want to talk about is this. Data for binding energy per nucleon or some nuclei are given here. This is Be per nucleon. Find out the Be per nucleon of nucleon X. Sorry, yeah. Find out the Be per nucleon of X, which you just did here. So if you know that neutron is actually a nucleon itself, just like I explained to you, neutron is already a nucleon. You cannot separate it into any more nucleons. So binding energy by definition would actually be 0. Okay, so it's 0. There's no workings, there's no method to show. It's straight away 0 because you cannot separate a nucleon into another nucleon anymore. All right. And then the next question here is calculate the energy change that takes place in this reaction. Okay, so from these two, which is your reactant, to your product here, they want to find out your energy change or rather your energy release. Okay, so as I mentioned to you just now, you could probably use E equals to delta mc squared, provided you know the complete value of all the masses. But here you see, the question never gave you any information about the masses. You do not know any masses here. So you cannot use this method because you do not have enough information to go with it. So the only way you can go about the question right now is to use the other method where I told you the energy change or rather your energy release will be the BE of your product minus the BE of your reactants. So looking at it in the form of an energy level diagram, this is what you see. Energy at infinity, energy of your reactants, energy of your products. Okay, the BE of your reactants is this. The BE of your products is this. The difference in their BE is actually your energy release. Okay, so here you can actually find out the energy release by taking the BE of the products. So same thing as before lah. You already know that BE is actually nucleon number multiplied by BE per nucleon. You take the BE per nucleon multiplied by nucleon number, you're gonna get your BE itself. Okay, so for product, it's just going to be helium. That's why it's 4 times 11.3290. For reactants, it will be for deuterium and tritium. This is what you're seeing. Deuterium is nucleon number 2 multiplied by 1.7813. Tritium is nucleon number 3 multiplied by PE per nucleon of 4.5285. Okay. Yeah, don't forget that you have a power of 10 here. Okay, you have a power of 10 or 10 power minus 13. All right. So put that in, eventually you get your answer as 2.82 times 10 power minus 12 joules. Okay, so this one should be fine. Just like that. Okay, the difficult part is the next one. They are asking you right now, use your answer in part 2 to determine the energy released when 2 grams of deuterium reacts with 3 grams of tritium. Okay, so here they actually gave you the masses of your reactants. Okay, so think of it this way now. So you see right now your reactants, deuterium, tritium. Okay, so it's correct to say this, right? I mean, yeah, I think I wrote it here already, so I better just make use of that. The nuclear equation that you saw just now was this. One atom of deuterium reacts with one atom of tritium to give you whatever you have here. And the process, it gave you 2.82 times 10 power minus 12 joules of energy. Okay, the thing that you need to realize here is one atom of deuterium reacts with one atom of tritium to give you this amount of energy. Okay, now when you look at what is stated here, they told you 2 grams of deuterium reacts with 3 grams of tritium. So how many number of nuclei do you actually have here for deuterium and tritium? Okay, now this one will probably have to relate to what you probably learn in chemistry. You see, if I give you deuterium 2,1, yeah, this one I know is nucleon number. Okay, this is what we've always said. But we can also say that this is the mass in gram of 1 mole of deuterium, right? I mean, there are two meanings to this number here. The one that we commonly associate with was that this one is actually telling you the nucleon number. But in chemistry, I think you guys learn another thing to this also. If you want to know the mass in gram of 1 mole of this element, this one is the mass. So here, the mass in gram of 1 mole of deuterium is actually 2 grams here. Okay. I can also say the same thing for tritium. My tritium is 3,1 here. So looking at this one, 3, the mass in gram of 1 mole of tritium is actually 3 grams too. Okay. So the thing that you just need to see here is this. You see, they already told you 2 grams here. I have 2 grams of deuterium. I have 3 grams of tritium. This one already indirectly tells me that I actually have 1 mole of deuterium reacting with 1 mole of tritium. And coincidentally, 1 mole has 6.02 times 10 power 23 nuclei. The same also goes with tritium. Okay, so if you want to find out the energy release, you actually take the Avogadro constant, which is basically the number in 1 mole, multiply with the energy release for 1-to-1 interaction. Okay, 2.82 times 10 power minus 12 is this one. Is when 1 molecule of deuterium reacts with 1 molecule of tritium. So now you have 1 mole of them reacting with each other, This means you have 6.023 times 10 power 23 reacting with each other. All you just need to do is multiply whatever energy you found initially with that amount. Then you're going to get the answer as 1.7 times 10 power 12 joules, just like that. Okay. Right, so this one is okay. Then after that, there should be one last question I can do before I move on to the remainder of your notes. Okay, so this one is okay.
Yeah.
All right. Okay, there's one more question. Let me just go through that one question and then we'll be done with this. Is it 20? No. Is it 17? Is it 17 or 18? 18, I think we've done. Yeah, I think we've done 17 of this. Okay, so we'll just do one last question before I move on to your notes. Okay, have a look at page 17. Okay, let's have a look at page 17. Your notes. Mark 17 key photo. Okay. Mark 17 key photo. Okay, the first question started off with define what is meant by binding energy of a nucleus. So this one is something that is readily available from your notes. Energy needed to separate a nucleus into individual nucleons completely to infinity. Okay, so the keyword here is nucleons completely to infinity. You must have the word to infinity. This is where your 1 mark comes from. And then the next one is energy needed to separate nucleus. This is where your other mark came from. Okay, you need to have that too. Okay, so that one should be okay. It's just a simple definition from the notes. Okay, right. Then after that, we go on to part B. All right, part B, this one's slightly a bit different. Now, they tell you right now that you have a stationary nucleus of uranium-238 that decays to form a nucleus of thorium-234, and alpha particle and a gamma ray photon are emitted. The equation representing the decay is shown over here. Okay, the masses of the nuclei are given in this table here. And the next thing they'll ask you is this. State the relationship between the binding energies of nuclei that is consistent with the reaction being energetically possible. You need to make reference to the binding energies of the nuclei involved right now. This one. What can you say about the binding energy of the nuclei so that the reaction is energetically possible in the first place? Okay. So this one, it will kind of relate to what I just mentioned to you earlier. Remember just now I told you in any nuclear reaction, the nuclei will always change from an unstable to stable state to become more stable. This one I told you just now over here, the goal of any nuclear reaction is to become more stable. That's what a nuclear reaction always does. That's why a nuclear reaction happens in the first place, because it wants to become more stable. Okay, so it goes from an unstable to stable state. It means that in terms of an energy level diagram, it actually goes from a higher to lower energy level. All right, so represented in an energy level diagram, this is what you're going to get. So I drew for you 3 lines before this. The topmost one is actually infinity. Then after that, you also have the lines representing the reactants as well as your products. Products generally will be lower than your reactants because it's supposed to be more stable. It's supposed to be at a lower energy level. Okay, so here, look at the BEs. So this one is BE of your reactants. This one is BE of your products. Okay, so if your reaction were to occur, what can you say about the BE of your reactants and BE of your products? So the thing here is that for your reaction to occur, BE products must be more than BE of reactants. Okay, because if you want the reaction to occur now, you can clearly see that if you were to compare the BEs of reactants versus products, BE of products must be more than BE of reactants. Okay, that's why your answer here was this, which is stated as this. The total binding energy of thorium and helium nuclei, which is actually your products, must be greater than the binding energy of your uranium nucleus, which is actually your reactant. And if you want your reaction to occur energetically, your binding energies must be this value. Okay, right? So that one is okay. Right, so this one is one thing to see from here. Okay, so I'll just clear this one off. Then after that, they ask you to calculate for this reaction the change in U of the mass. So change in the mass is actually difference in the mass of the reactant and products, which you have over here. So you just take the difference, and then eventually you get the answer 4.59 times 10 power minus 3 U. Okay, so don't round up in the middle of your workings, only round up towards the end when you got your final answer. That one should be fine. Right? So if after that one is also okay, then we move on to the energy release. Now for your case, the energy release, you can actually just use delta MC square. Okay. The mass you have, 4.59 times 10 power minus 3, it was in terms of U. You need to change to kg. That's the reason why you multiply with 1.66 times 10 power minus 27. This one is from U to kg. Okay. Then you just multiply with the speed of light, square it. You're going to get this final answer. 6.86 times 10 power minus 13 joules. Just like that. Okay. Right. So this one is also okay. Okay, then after that, the last statement here would be this one. Yeah, so this one is okay, I hope. Now, the last one is state and explain whether the energy of gamma ray photon is equal to the energy released in the reaction. Okay, now since you were doing something about duality in school right now, you probably already know what on earth is a photon, right? A photon is actually a packet of energy of EM radiation. Okay, so since you are doing this in school right now, you should know what's a photon already. So the question is just asking you, is the energy released in this reaction solely equal to the energy of your photon? So you look at your current equation. This one is your photon, gamma ray photon. You know is a packet of energy. It is an energy in itself. So the question is just basically asking you, if you go from reactants to products, you have energy release. Say maybe, for example, just for the sake of discussion, maybe I tell you you have 1,000 mega EV. Would your photon be carrying this whole 1,000 mega EV of the energy release? The answer is actually no. Because when you have energy release, say for example, it's 1,000 mega EV right now, that energy is actually divided between the three products that you have. Okay, it will be divided with tutorium, to alpha particle helium, as well as your gamma ray photons. Okay, it will be split between these three things. Okay, so in your case, the energy part of it will go into thorium and helium. It will actually be in the form of kinetic energy. Okay, so it will actually be correct to say this. Thorium and helium nuclei have kinetic energy. It's actually taking part of your energy release. Therefore, the gain energy of your gamma ray photon will be less than your total energy release. Okay, so this is the answer. You just need to say that thorium and helium have kinetic, so energy of gamma ray photon must be less. The underlying understanding here is that you need to know that all the energy, part of the energy must have gone to KE. So whatever your gamma ray gets will not be the total energy release. Okay, have a look at page 15. This is November 16 P42. November 16 P42, last part here. To look at it this way.
Yep.
Okay, right. To tell you, phosphorus 30 was the first artificial radioactive nuclide to be produced in a laboratory. This was achieved by bombarding aluminium 27 with alpha particles. A partial nuclear equation to represent the reaction is given by this equation here. State the full nuclide notation for alpha particle. Meaning to say, write them down with the proper symbols. Alpha particle can be written as helium-42 or just alpha-42.
Yep.
And then what is the symbol represented by this symbol phi? You actually have to kind of work it out what this particle actually is by balancing out the proton number and nucleon number. If you know the alpha particle is 42,
the photon.
this one you go and balance it out. This one will be neutron. N0, it's not proton. Proton is this one. Proton is 1, 1.
Oh, okay. Yeah.
Neutron is 0, 1. Okay,
Mm-hmm.
so it's neutron. The full nuclide notation of a neutron is going to be this 1, 0, N. Okay, right, so that one is okay. Then after that, they ask you, data for the rest masses of the particles in the reaction are given here in this table. Calculate for this reaction the change in total rest mass of the particles. So basically what you just need to do is that you group out the masses of the reactants and products, you find the difference. Okay, so same thing as before, make sure you use the full values that are given inside the table, don't ever round it up. If you use the full values, you sub in this equation to find the mass of the product and mass of the reactants, you should eventually be able to get this answer. Your mass defect is 2.84 times 10 power minus 3. Okay, so this is your the change in rest mass of the particles. Okay, so your product is this. Okay, I'll just find it. This one was your product. This one was your reactant. Okay. Then you get the mass change as 2.84 times 10 power minus 3. And then after that, they ask you to calculate the energy in joules equivalent to the mass change calculated in 1. Your mass, the energy in joules equivalent to your mass change calculated in 1. This one you have to use, since you know the mass effect, if you want to find out the energy equivalent to this mass defect, you can use E is delta mc squared. You realize that there's a change in mass, there must be energy here. So what is the energy corresponding to that change in mass? You use E equals to delta mc squared. So delta m is 2.84 times 10 power minus 3. Remember to change to kg. Okay, remember to change to kg. This one is actually U2 kg. Gonna multiply with speed of light square, then you're gonna get the energy is 4.24 times 10 power minus 13 joules. Okay. All right, then after that, they will ask you, with reference to your answer in B1, comment on the energy of the alpha particle such that the reaction can take place. Comment on the energy of the alpha particle such that the reaction can take place. Now, they're asking you to refer to B1, which is this one. B1 was about you finding the masses. So what you want to do here is that you want to actually compare the masses of the reactant and the product. So if you if you try to look at the mass of the product and the mass of the reactant individually, you will realize that the mass of the product is actually more than the mass of the reactant. Okay, this tells you that there is increase in mass. Okay, there's increase in mass. So when you have increase in mass, energy must have been converted to mass. Must have been converted to mass. This energy must be provided by something. Okay, so this energy must have been provided from a source. Okay, so the thing to realize here is that mass of product is more than the mass of your reactant. There's increase in mass here. Energy must have been converted to mass here. So the energy must have been provided from a particular source. Okay, from a particular source. Yeah, this is what I'll say now. Must have been provided by a particular source. So what you will say here is that you should have realized that the reaction causes an increase in the mass of the system. So that energy, the energy must have been used to convert it into energy must have been converted into mass. So where did this energy come from? You could say that the alpha particle that was used in the reactants must have at least this amount of kinetic energy. The energy actually came from the Ke of your alpha particles. Okay.
Okay.
In other words, it's basically this understanding now. The kinetic energy of the alpha particle is converted into additional mass during the reaction. Okay. Since you have an increase in mass here, that means mass energy must have been converted to mass. But where did this energy come from? The energy actually came from your Ke of your alpha particle. Okay, that's why we say here, your alpha particle must have at least this amount of kinetic energy.